So our motivation is detecting the sleep apnea, and it affects about 30 million Americans, which is almost 1 out of every 10 Americans. And these interruptions in breathing, known as sleep apnea, can occur multiple times per hour and last for 10 seconds or longer. When the brain realizes breathing has stopped, it briefly wakes the person to reopen the airway, often with a loud snort or choking sound. The cycle can repeat itself throughout the night, and the disruption to normal sleep leads to poor sleep quality, particularly by preventing the person from reaching or maintaining deep REM sleep. So that's the reason why we chose our topic as detecting sleep apnea.
So our proposed solution is to use an FMCW radar in order to remotely detect sleep apnea episodes. This is different from the current methods of detecting sleep apnea, which require sensors being hooked up to the patients over an entire night's time.
So there could be some challenges that we could face while we're detecting sleep apnea. Some of the big challenges could be making the radar really good at picking up small movements, or figuring out how the person is lying down when they sleep, and checking that it works well in different situations. Like when there are other people around, or when someone is sleeping with a blanket on them, there could be multiple challenges we could face.
So taking a closer look into our approach, we have as a first step the collection with the radar and the human. Then as a second step, obviously, there is a conversion from the raw analog signal to with the analog to digital converter to data that is usable. Now with this usable data, we can take multiple FFTs in order to get both the Doppler over time graph and the range over time, and analyze the phase as it changes over time in order to get an idea of minute differences within a specific range bin. Then finally, we will use a pattern recognition algorithm in order to determine the rate of breathing and hopefully have a clear idea of when a sleep apnea episode is happening. So our video here puts our data collection methods on display, as the user is a fixed distance from the radar that is collecting data, and they are breathing at a fairly constant rate. Now after about 10 seconds, you can see the rate of breathing increases, and finally at around the 20-second mark right now, the rate of breathing ceases, indicating a sleep apnea episode. So the idea is to be able to differentiate these three different states of breathing.
So this graph is the main result that we're expecting. So we tried to observe the phase shifts over time using raw ADC data, and we classified into three different sections. For the first 7 seconds, normal inhalation and exhalation were shown on a graph, followed by a faster breathing rate for the next 7 seconds. For the final 7 seconds, the phenomenon of not breathing is demonstrated through the graph. And yeah, that's what we're expecting.